Thank you very much for joining us this afternoon for this webinar as part of the Energy Pathfinder project. My name is Kenny. I work for Historic Environment Scotland, one of the partner organisations in the project. A little bit of housekeeping first of all. The webinar is going to be recorded today, just to make everyone aware of that at the outset. We're expecting the talk to be maybe 40 to kind of 45 minutes. If you're not asking a question, please keep yourself on mute as per usual. I think because we've got a relatively small group this morning, questions during the talk are fine. Just please raise your hand and Chris will come to you when we get a good juncture. An introduction to Energy Pathfinder, first of all. So Energy Pathfinder is funded by the European Regional Development Fund through the Interreg Northern Periphery and Arctic Programme. It's a project looking at appropriate and effective retrofit pathways for traditional buildings across the northern periphery of Europe, and also has an interest in building monitoring, in simulation, and in co-design. We're delighted to have with us this morning Mr. Chris Morgan of John Gilbert Architects. Chris is an architect and director at John Gilbert. He's got over 30 years experience in ecological design and sustainable development, a range of experience which includes master planning, energy infrastructure, award-winning architecture, research and teaching. He's previously been a chair of the Scottish Ecological Design Association and is one of only 4 architects to hold the RIAS Advanced Sustainable Architecture accreditation. He's also a design review panelist for Architecture and Design Scotland and a certified Passivhaus designer, and also certified in building biology and permaculture. So without further ado, Chris, I'll hand over to yourself.
Thank you. Thanks, Kenny. Let me just check this works. Okay, can everybody see that okay? And hear me okay? Right, okay. Right, thanks for asking me to be involved in this. That was a nice introduction. I'll crack on. This talk is in 3 parts, and about a half of it is the case study at the end. But because so much of what I've been talking about is the reason for choosing EnerPhit is a critique of the normal way of measuring energy efficiency. So a big chunk of this is about ISH2. Now, if a number of you are in Ireland, ISH2 is the energy efficiency standard for social housing in Scotland. So there'll be an equivalent in Ireland, I would imagine. So it's a brief discussion of what we consider to be some of the problems with ISH, and then why we think EnerPhit and the ACB standard, which are a sort of close cousin of EnerPhit, point the way forward, I think, more meaningfully for how we should be doing things. So a little bit on ISH2, and apologies if ISH2 isn't familiar to you, but I would imagine something similar exists. This is the Scottish Government's proposal for improving energy efficiency in Scotland, and it's good in that it looks at all the different types, all the different sectors, all the different tenure types. So the bit about social housing is there in the red highlight, and the basic deal is that you have to get to EPC B by something in the 2030s. So the Scottish Government has tried to get one over on the English by saying net zero by 2045. Most tenures, they say, want to be C by 2030-ish, but social housing is leading the way and will be grade B, and I'm sure you're all familiar with that. There's more of a focus than there was previously on zero carbon heating systems, i.e. largely heat pumps, but not entirely. There'll be no more gas boilers in new homes, as we know. The strategy that they've produced is actually pretty comprehensive, and as I say, it does deal with multi-tenure, and it's quite realistic. There are quite a lot of get-out clauses, so technically feasible and affordable are 2 phrases which are used and are particularly relevant to people in the heritage network, because it's clear that we can't necessarily start chasing these sort of high grades in older buildings necessarily. It may be possible. So the 2 concerns we have, there's quite a few concerns that we've actually got, but I'm only really going to talk about the top 2, the pace of change and the performance gap, which I hope you're all familiar with. But taking a step back, this is what we probably ought to be doing, or something like this. It's a very, very dramatic drop in carbon emissions. When we compare that, which admittedly is a just the way the graph shows. You compare that with what Scotland's achieving. This is Scotland, I should say, not the UK. This is how we're moving forward in Scotland, and I'm not saying it's a bad thing, because it's better to be improving than not, but it's a glacial rate of change, rate of improvement. So I think nobody could look at what we need to do according to the scientists and what we are doing and go, oh, we're absolutely on track. You know, I don't think anybody could say that. The other issue is that we don't know what we're talking about. For those of you who are familiar with performance gap, apologies for the next 10 seconds, but the performance gap is really important because, well, I'll tell you the story. These two graphs tell the story. The graph on the left, the top bar is, well, the top two bars are the estimates of both gas and electricity that were going to be used in a building which subsequently won Green Building of the Year, Green Building Challenge or something like that, a few years ago. And it won that at least partly on the strength of the fact that those numbers were so much better than the good practice benchmark, which we can see below it. So everybody looked at those design estimates, and this was one of the first examples of this thing called the performance gap, where what we say as architects or energy consultants and what actually happens are two completely different things. And the trouble is, of course, that, you know, it's not that funny, because actually the climate, you know, doesn't care what we say about it, it cares what we actually achieve. The graph on the right is a similar study that was done at around about the same time, measuring a number of different houses, dwellings, and you can see that what was predicted was the sort of purple bar, and what the houses actually achieved was in many cases quite a lot more. But what it does is it establishes the fact that what buildings tend to do is consume more energy than we predicted they would, and that's obviously a bad thing. In general, according to people who do passive house and things like that, the actual consumptions are generally about 60% greater than predicted, but it varies enormously. And the trouble with this is that we don't, the thing is that when we talk about energy efficiency and we use the normal, the EPC ratings and SAP and whatever, I think you've got SAP in Ireland, haven't you? I think it's the same thing. But the trouble is that if you have a measurement technique which isn't accurate, then you don't really know what you're talking about ever. And that's a major problem for anybody trying to meaningfully improve energy efficiency. So we can't control something we're not measuring accurately. This is a really useful graph, and it shows about 400 houses that were measured in reality down in England somewhere. And they measured the actual energy intensity against the prediction of their EPCs. And what you can see is, obviously there's variability, but you get the average numbers there. And what we can see is that, broadly speaking, the SAP ratings which predict, for example, a significantly better performance in a C and B than a D and E, it's just not happening in reality. So I think this underscores the fact that when we use SAP to measure what we're doing in energy efficiency, we're not using something accurate. We can't be confident about it, even if it's sometimes right. The other thing about that is that because of the way that SAP works is we lose the renewables in this. So these aren't actually measurements of energy efficiency, they're measurements of overall energy consumption. So there are plenty of reasons, I believe, to be suspicious or at least cautious about the SAP ratings, the EPCs and all of that sort of standard stuff. So if you compare this, just have a look at the numbers. Those numbers are 150, 180, 200, they're those sort of numbers, right? This, some of you may have seen, is a similar graph that measured what actually happened in a number of passive houses in Germany a few years ago. Now, the first thing that's worth saying is that they're relatively accurate. Also, the average is achieved, but look at the numbers on the left, and it's not an exact correlation, but the numbers here are 15, they're not 150. Now, it's measuring a slightly different thing, but the point is that we're talking about a graph which is 10% of what the other graph was, roughly. So there is good reason to suggest that this is going to work, and what this graph is used for is to say that what was predicted and what was actually achieved on average was the same. Now, this is quite an old graph actually now, but this is how it's happening. What we're doing is we're taking the biggest energy consumption blocks, and we're reducing them significantly. And when people talk about 10%, when I talk about 10%, what I'm meaning is this reduction from roughly 150 to 200 to roughly 15 for passive house. As most of you know, we're looking at sort of 15, 20 for our space heating requirements, and then also water heating requirements. So we're not trying to achieve zero. I think trying to achieve zero is a bit of a game. I don't think it's a meaningful thing to play, that game of net zero, but it is meaningful to say we need to use massively less energy than we are now. The reason I think 10% is about right, many years ago, some of you, this was doing the rounds in sort of the 2000s. There was an idea which attracted a lot of attention, and I always thought it was a good thing, called contraction and convergence. And what it was attempting to do was to say, well, how much energy can we use? What can we afford to do? What represents sustainability? Is a 20% reduction on what we do now, is that sustainable, or is that just like better? I don't know. You know, what's the number need to be? And it was very useful because it gave us an area to aim for. And what it amounts to is, well, there are two parts to it. One is that we all need to use less, but clearly across the globe, we use energy at significantly different intensities. So America is the biggest culprit, but other countries or other areas like India, they can actually afford to use more if we were going to be equitable across the world. So in the case of Britain, we're B, and we need to be down at roughly 10% of what we're currently, or what we were using at the time. So 10% is a rough guide as to what represents sustainable buildings, in my view, very roughly. I don't think it's worth getting too upset about numbers in sustainability, but it is worth getting a rough idea so that you can aim for these things. And we do know that passive house buildings work. These are new buildings, which I studied for a long time. So I worked at the School of Art in Glasgow for a few years, and we monitored energy efficient houses, including passive houses. The four that are there are the ones that you can see, you know, amongst all of the energy efficient houses, they were certainly the best. And the worst of those was a bit of an anomaly, to be honest. So we know passive houses work, and we know that they're consistent. Consistent performance against their prediction, I think, is what I'm getting at. So the level of aspiration is about right, and we know that when we design them correctly, we'll get roughly what we intended to get. So that's why the passive house approach and EnerPhit, which is its retrofit cousin, is a sensible option for us. However, there is no doubt that EnerPhit is costly, and it's not always possible. I mean, there's a building we're working on now where we just can't achieve EnerPhit, and I'll tell you a tiny bit about that later. And it's worth noting that two organisations have modelled this, and I would imagine that the Energy Pathfinder, that's being done as well. I don't know, but both the London Energy Transformation Initiative and the ACB have modelled what we should do across the housing stock in Britain, at least, and the sort of numbers we need to be aiming for. And as a result, they've come up with this ACB retrofit standard, that should say, not strategy. One of the things that's important about it is that it uses the same mechanism, PHPP, as EnerPhit, so that we can accurately predict what's happening. And it's probably fair to say the performance level that we're aiming for is about 30% of normal. So it's not, in my view, quite as good, but it's, you know, it's obviously a lot better. This graph comes from Letty. Some of you will know this, London Energy Transformation Initiative. The circles are my imposition on it. So, but it's just to try and give you a rough idea of what we're aiming for. So the blue bars on the right are the energy consumption of all of the buildings in Britain, basically, arranged broadly over the 100 to 150, 160 kilowatt hours per square meter per annum. And what Letty believe is that we should be shifting all of those blue bars to, broadly speaking, all of those orange bars. So if we take the red circle, which is roughly what you'll find on average houses are using, particularly in Scotland, because it's a bit colder, it tends to be a bit higher energy consumption. If we use EISH as our guide, EISH 2, we will get to round about where the orange circle is, and we'll spend quite a lot of money doing that. I mean, you know, 15, 20, 30 grand a property, which is quite a lot of money. And we'll get to probably the orange. What it will tell us we'll have got to is around about 50 or 60 or maybe 70. But what in reality it will be is probably around about the 100, 110, 120 sort of mark. So we'll be spending a lot of money, and we won't really have got that far, to be honest. And we certainly won't be far enough. If we go for the ACB we'll probably get to, well, we will have to get to the pale green circle, which I would say is bang in the middle of where Letty and to an extent the ACB think we should be. And if we aim for EnerPhit, or if we achieve EnerPhit, we will be right at the top end of the orange bars, so where the darker green is. So I find that the most useful way of trying to describe what we should be aiming to do and the context within that, because I think everybody's spouting out numbers and sort of guides and saying we've saved these many London buses full of carbon, and nobody has a clue what it means. So I think it's quite good to get some context. So for me, that's a very useful graph. But note that the circles are my my gloriously amateur intervention onto that. And again, a little bit more formally, this is what we're talking about. So hopefully most people are familiar with EnerPhit. If you're all involved in an energy efficiency project, then I would imagine you do know what this means. The ACB is broadly less rigorous, requiring less air tightness, lower heating demand, but it does have a number of more specific get-out clauses, which are useful particularly for heritage properties, but for others that by dint of form or shape, it just are just not cost effective to make better. There's a few things that are worth talking about there, but I won't go into that. So this project on the right is is the next project after Niddrie Road, and we will be making this an ACB retrofit standard project. And I think that we might find that is actually more helpful to the industry in terms of what we're aspiring to do. But we'll see. But we did look at modeling that to achieve EnerPhit, and it wasn't possible. And the reason it wasn't possible is because on the two faces that you can see on the top screen, we're clearly not going to insulate the outside of that stone. So that has to be internal, and there are limits to what you can do internally on internal wall insulation before you create too many problems. And the wall at the back, which isn't a very good photo, but if you can see, you can't see, but that rendered sort of gable that you can see at the bottom there, that's the back wall. And we initially thought, well, we'll just put external insulation on that, but we're not allowed to. It doesn't belong to the housing association. So we're actually left having to internally insulate everything. And there are limits to how much insulation we feel you should put on a building like that before you create too many moisture and other problems. So we're limited in what we can achieve. And as a result, the ACB standard represents a pretty good standard for us, I think. So that's the sort of bit of context. I hope that's useful, but that's why we want to do EnerPhit, why we think EnerPhit is useful to us. So the rest of this is just about Niddrie Road, which isn't quite finished yet, but it's nearly there. It's about a month away from completion. The interesting thing about Niddrie Road is that when we got hold of it, or when the Housing Association got hold of it, they owned all of the flats, or they very quickly owned all 8 flats, which is unusual. They also were all void, or one wasn't, but then the woman left. So it's very unrepresentative insofar as we owned all the client owned all flats and they were all empty. So we've had a lot of time to faff about and muck about with this building, which just simply wouldn't normally be the case. So it's at one point very unrepresentative, but in other ways, perfectly normal. We actually provided 3 options for refurbishment: a standard refurbishment, a sort of whole house, a more holistic one, and an EnerPhit. And they actually opted for the standard one. But what then happened was that we won some money from the Scottish Funding Council to demonstrate best practice. And so in a bit of a rush job, it was upgraded to EnerPhit in order to have something meaningful to say. So because of that Scottish Funding Council money, this project was upgraded to being a more interesting thing. That's the context. You can see it in the middle there. That's the view from the south. And those of you with a mind towards sort of passive solar and such like will immediately realize it's an atrocious example of passive solar building. So this is what we're dealing with, that building in the middle with the lines around it. It's heavily overshadowed by the adjacent buildings and the trees. It's got very small southeast facing windows only, which is where we're getting our solar gain, which is where we're trying to offset fossil fuel use. Conversely, it has huge northwest facing windows onto the street, which lose enormous amounts of heat. And there is significant unavoidable thermal bridging. So whilst in many ways it's an excellent example, it's a very difficult example to pass. So one of the things which is often forgotten is that this is probably one of the hardest buildings you could make EnerPhit because of its lack of solar gain. So if we can do it here, we can do it anywhere, sort of thing. for a variety of reasons, it needed a considerable overhaul. There was a lot wrong with the building anyway. So you can see from the photo on the right that once we stripped back, we realized how much needed to be changed. So, you know, it had been left for a long time. It was in pretty bad state. So hundreds of thousands of pounds were spent just doing what Historic Scotland always tell us to do, which is simply to maintain the building in good condition before you start mucking about with insulation. And as a result, the project became more expensive the more we knocked out. But you can see what's going on there. We stripped back the back walls so that we could, because we're trying to achieve air tightness. So it was a complete overhaul, full strip out of all services. Some, which is probably more accurate to say, lots of urgent long-term maintenance. And then we agreed with the client that not just an energy efficient building, but also a building with consideration about air quality and a more holistic approach to fabric was what we were going to do, and they were okay with that. Partly because they didn't fully understand what we were asking them to achieve. The main picture on the right is just to show that there were quite a lot of structural things that we had to do as well. There were some entertainingly dangerous looking bits of stone that were falling off. And so we had quite a bit of work to do. The other thing which is important to me, but tends to get missed out by other commentators because it's all about carbon, is that there was an existing quote in place for £36,000 worth of chemical treatments to be sprayed all over the building because of the rot. Oh no, that's not true. There was about £20,000 of chemical treatment and about £16,000 of timber replacement. There were Bessemer beams that were decayed and so on and so forth. And I have a long-standing hatred of chemical treatments. Was heavily involved in a lot of sort of healthy building type stuff over the years. So we got the chap who's pointing meaninglessly into the air to come and give us a building pathology sort of report on how we could avoid using any of those treatments. So we haven't used any chemical treatments in the building. We have repaired all the timber that needs repaired, and we have created a breathable and relatively safe environment in terms of moisture conditions, humidity conditions. So we won't be needing any of that chemical, those chemicals. And for me, that's a big win. This is, in short, what we have done to the building. This is a sort of cutaway looking from the back of the building. So what you can see, so starting at number one, we've insulated the roof. There'll be photographs of all of this, but this is to give you an overview. An additional piece of work that we wouldn't necessarily always do is that we have to make sure that the roof insulation meets the wall insulation. This is one of those bits which is EnerPhit rather than just normal retrofit. Normally the roof insulation will do its thing and then the wall insulation will do its thing, and there will be a gap between them at the eaves, and we can't have that in EnerPhit. We have to make those meet because it's a heat loss and mold and decay risk. So the bottom set of slates were stripped off, and you know, all of the woodwork at the top of the wall head was checked and all the rest of it, and quite a lot needed to be repaired. So that's number two, where we made sure they met and tidied everything up. We increased the size of the windows in the back because they were really quite small, and we need as much solar gain as we can possibly get into this machine for living in. We put in new triple glazed windows, as you would expect, and we externally insulated the back wall and the gable. We then introduced mechanical heat recovery, as is required in a passive house type building. And we also introduced wastewater heat recovery because it's an easy win, and the biggest heating load in those flats would become water heating once we'd done the passive house work that we were doing. On the street side, which is sort of facing away from us, we have internal wall insulation, which is relatively restricted, and I'll talk a bit more about that. Then we did an extensive amount of repair, stone repair and repointing and so on that street side, to make sure that wall was as robust as it could possibly be. First floor joists were removed on that side after lengthy shenanigans with woofie, which I'll talk about. The layout was changed, and the ground floor was heavily insulated, and I'll talk a little bit more about that. So I hope that gives you an overview of what we did. It's all sort of normal stuff, but just thicker and more complicated than normal, I think. Just to note that we took some considerable care over the stonework on the face of the building. I know that a number of people in the heritage world think that, you know, energy efficiency is all about just stuffing insulation and polystyrene in, but it's actually important for the energy efficiency to work that the building is in good condition, and so that's part of what we were doing there. And then the 5 aspects of passive house design that I imagine that you're all familiar with, but lots of insulation, no thermal bridging, air tightness, triple glazing, and MVHR, and I'll zoom through those. Air tightness, you can see on the right, was achieved rather than using membranes, which is more common in new build. We took the view, well, I took the view, that a nicer and probably more robust way to achieve air tightness in an old building is not with plastic membranes, it's with lime plaster. And there are a number of other advantages of doing that, but if you want a long discussion about air tightness and lime plaster, then feel free. But I mean, for me, this is a really good way of doing it, and it stops a thing called thermal bypass, which is air that it's not air tightness. It's a cousin of air tightness, where the air gets into the construction but doesn't necessarily get into the room. And some of you probably know about that. But the thing about plastering straight onto the wall is that you get air tightness, but you also remove any form of thermal bypass. So there are quite a lot of advantages. And obviously, using lime plaster rather than plastic membranes is, to me, a more intrinsically heritage-based way of solving a problem, and I prefer it. Belt and braces, though, they taped all the corners for potential cracking. And the window detailing you can see here, so you can see it's triple glazing, and you can see how the insulation was taken over the face, either internally or externally, to ensure that there wasn't any thermal bridging or air leakage at the window surrounds. Hopefully that's familiar to most of you. We then have the issue of thermal bridges, which is the normal issue of retrofit. And if you're all involved in a retrofit project across Europe, you'll be familiar with these concepts. But these are the ways we dealt with them. Essentially, we're trying to close off all of those gaps, the gaps you can see between the red bits of insulation. And an example on the bottom left there of what we do at that bottom left bit. Oh no, sorry, I forgot that I added the slide. So this is the 2 types of insulation. So on the left is the internal insulation. Now the internal insulation, by putting insulation internally, we know that we raise the risks of moisture damage in that wall. And so that insulation has to be vapor permeable. So that's wood fiber board screwed directly through the lime plaster and into the stonework. And on the outside, it's not such a big deal. And so we've used mineral wool, which is considerably cheaper to use. Well, it wasn't that cheap, but the moisture risks are much less obvious on the, or well, they don't exist really on the outside, on the external wall insulation. That's the insulation to the loft. So it's it hasn't been completed yet, but the principle there is that we created a framework so that you could still walk on it. And the other thing that we've added is a membrane over the top, which hasn't been sealed down yet, but underneath that membrane is about 450 mil of insulation. But the point of adding the membrane is to prevent a thing called wind washing, which some of you may have come across. It's where the heat is sort of whisked away by air movement. So we want a healthy breeze in that loft, but that healthy breeze, we know, reduces, well, it sucks the heat through the insulation. It actually sort of forms a sort of suction through the insulation. So we lose a lot more heat again than we thought we were going to lose, but we can stop that from happening by putting obviously a breathable membrane over the top. That is a thermal bridge, a classic thermal bridge per a conventional retrofit project. There's insulation in the floor, fair enough. There's EWI on the wall, fair enough. But there's a significant thermal bridge there, which you're probably all familiar with. How can we fix that? We can fix it like this. So just sort of going between the two, we extend the external wall insulation right down and into the ground as far as we can go. But as you'll be aware, we've also got a cold solum. So we had to insulate on the inside of that, which annoyed everybody, absolutely everybody. So we've increased the insulation under the floor joist, and then we've taken that insulation down the inside of the wall. And the reason for doing that is partly to stop losing heat, but it's also to achieve the thing. So if you look at the therm calculations on the right there, the number that matters, and the bit that matters is you can just see there, just to the left of the wall, it says 14.93 degrees C. What we did was we extended the wall insulation down until we got a number like 14.93, because what we're trying to do is, we're trying to save heat, but we're also trying to make sure that the internal surface temperatures are warm enough, because under those conditions, we can be certain that we won't get any mold or condensation. And that little corner, that skirting board in the corner behind the sofa, that'll be the bit that gets mold if we get it wrong. So if we can get that surface temperature up to 13, 14, 15, we know we won't get mold, unless something spectacularly stupid happens. But under normal circumstances, that'll be fine. So we're doing this not really to save heat, but to achieve these internal surface temperatures, which is broadly a health thing and a sort of fabric decay maintenance thing. As I mentioned, the wall insulation and roof insulation often doesn't meet, and you can see here that we've got the wall insulation coming up from below, we've got the roof insulation or the ceiling insulation coming in from the left, but they're nowhere near each other at the eaves because of the way this building was built. It's very strange construction. I've not really seen it exactly like that. There was a sort of internal lintel that you can see there, which sort of took the roof, and then there was this very strange, purely uninsulated sort of lead ledge that ran between them, and it was it's kind of total pain to do. Anyway, so we just had to throw a huge amount of insulation into that corner, which is a bit of a shame, but it had to be done because we cannot have thermal bridging in those corners. So that's what it looks like internally. I mean, it all looks a bit heavy-handed, but once it's plastered, and it's fine. But that's the internal sort of implication in real life. And externally, you can see what's going on there. We've had to sort of strip everything back and extend and build this sort of insulated ledge thing that goes across the top there, so that we close the gap between the roof and the wall insulation. I hope that makes sense. We also did something that I've been meaning to do for about 20 years, which is put a lead soaker under all of the gutters. I've tried for years to get people to agree to put lead soakers under the gutters, because we see it so often that the gutters leak and then it just leaks into the stone. And then you have this sort of permanently saturated stonework for decades because nobody can be bothered to deal with it. But we managed to persuade the Housing Association in this case to put a lead soaker under. So even if the gutters fail, it won't damage the stonework. And again, this is not really EnerPhit. This is about trying to look after buildings sort of intrinsically as well. This is at the back. We had the same problem. The roof just didn't meet the wall in terms of insulation. So we had to build this slightly strange sort of insulated ledge thing. Which I must admit I thought was going to be a nightmare for the builders. When I drew that, I remember thinking they're never going to build that properly, because I've been a builder and I've seen what happens when architects dream up ridiculously complicated things and expect everybody to follow their logic. But we went through it in quite a lot of care and attention with them, and they did actually a fantastically good job. So fair play. They did a really good job. It's nicely finished. I wrote a few years ago this book, Sustainable Renovation, and in it we proposed, what's happened over the years is I've seen people slap polystyrene on the inside of a wall and said, you'll like this, Chris, you're an eco-architect, you'll appreciate this. And I've looked at this polystyrene and I've just thought, oh my God, it's just a disaster. You know, there's so many ways that doesn't necessarily solve the problems you think you're solving. And so one of the images that have been in my head for years was sort of this image, which we finally got to draw and put in this book, Sustainable Renovation. So if anybody's interested, there are two, in principle, identical wall insulation details, one of which has 18 problems, 18 reasons why you won't get the energy efficiency your SAP calc told you. And it also introduces health risks and building maintenance risks, because you've ticked a box on a SAP calc and that's really all you've ever done. And so that's the one on the right, which looks appropriately moldy and unpleasant. But it's a cartoon, but the point is to demonstrate that there are lots of things that can go wrong when you insulate buildings. And the corollary on the right is you can do something that's almost the same, but has none of the, well, all but one of the problems. One of the problems is you lose all the cornicing when you do this sort of thing, and that's the same on the one on the right. But 17 out of the 18 problems were fixed, basically. And so what's nice about Niddrie Road is it's the first time we've been able to build that detail, essentially. So the Niddrie Road detail is that drawing, essentially created, or more or less created. As I mentioned, we had to muck about with joists in the walls. So I'll explain these two graphs. We got WFI calcs, and I'm sure some of you are familiar with WFI. It's a hygrothermal modeling tool, and it's pretty good on the whole. I think that it has its failures. My own view is that it doesn't do well with air gaps. So if you introduce an air gap with WFI, it doesn't, it sort of stops knowing what it's doing, really. But I think if everything's solid and it's stuck together, it's pretty good. So we tested the various details at an early stage, and on the little graph on the right shows you that's the the back wall with the external wall insulation on it. And as you can see, it sort of fluctuates around 40, 50. They say relative humidity. I personally think that should be moisture content, but I was told it's correct to say relative humidity. But anyway, the point is, if it goes up to 80, it's a moisture risk, and it doesn't go anywhere near 80 over the long term. So that's fine. So we don't worry about the timber joist sitting in the wall at the back. However, on the wall at the front, where we have timber joist sitting in the wall, we can see that predicted by WUFI, the moisture content or relative humidity of that wall will fluctuate at quite high levels above or very close to the 80% mark. Well, in fact, they've put 85% there, but 80 would do it. Now, they've then, to try and help us out, they've put in 6 different options there. So I hope this is all making sense. Somebody shake their head or nod at me to tell me, Barry and Kenny, I can see your faces. So is it okay? Making sense? Yeah. Okay, good. We're trying to make sure that the moisture content in that wall stays below 80, and we can't achieve it in any of those scenarios. So those scenarios included different thicknesses of internal wall insulation. They knew it was wood fiberboard. And the people predicting this also wanted us to use storm dry, and I detest storm dry and will almost certainly never use it. I don't trust it. I don't think it works, even though in theory it's a phenomenally good idea. So we weren't going to do that. And so in the end, the only way to solve this, in my view, and I had to take a hit on this because we were already slightly over budget, was to accept that we would take all the joists out of the wall. The wall will be fine. It's just anything organic in that wall won't be fine at a continuous moisture content of 80%. So we took the floor joists out and did a new detail. And so this is the detail there, which hopefully makes sense to you. The floor joists, which used to just go straight into the wall, are now cut back. One good thing is that we're able to then introduce the air tightness layer right across that wall. So the lime plaster goes straight through it. We then introduced these, what are they called? Geocell, what was that stuff called? The foam glass blocks, which need to be pretty rigid. And then we put a beam onto that, and then we fix the joists back into the beam, basically. It's not that big a deal because most of it's taken by the Bressumer, but the principle is that, you take the joists out of the wall. Hopefully that detail makes sense. So we have a continuous air tightness and a continual level of insulation, and we have no organic material sitting in the wall anymore. And that way we can be confident, without using any dodgy chemicals, that we're not introducing a long-term decay risk for the client, whilst still getting an EnerPhit, within U values that are good, and so on and so forth. That's it with the insulation and the beam in place. That's that. And then this is the MVHR, all of which was introduced into a lower ceiling, which we put in the bathroom and the hall. And I think that's more or less it. So what have I said here? The 4 lower flats have an air source heat pump. There was an extraordinary situation where we had Glasgow City Council telling us that they would only fund this if we used renewables, and then Glasgow City Council planning telling us that we weren't allowed to use renewables. And so it was a ridiculous situation, but the compromise that was reached was that we used air source heat pumps on the 2 lower floors, because we could then not put the heat pumps on the building. So they were on the ground, and then we were just restricted by the length of height and depth, height and length that you can take your pipe work and so on. And so the upper floor flats have the gas boilers in as normal, but it's a bit of a shame. But what that does do is, because we are going to monitor the building, there's quite an extensive monitoring thing, which I haven't actually shown in this talk, but there is quite extensive monitoring. It will at least allow us to look at the differences between heat pumps and gas boilers in essentially identical flats. We introduced quick start guides, and there's quite a lot of sort of soft landings type engagement with the occupants. So we do quite a lot of that as architects, because having studied how buildings work in reality, one of the things that you see time and time again is that people not understanding how to use buildings is one of the biggest problems. So we do try to engage meaningfully with what's going on. We are confident that the EnerPhit approach will deliver real savings. Monthly heating bills reduced by roughly 90%. It'll depend on how people operate in the buildings. But I think it's fair to say that we're not likely to have fuel poverty in those flats, whereas I think that fuel poverty is going to be an enormous problem across Britain as a result of the recent energy costs. Warm, comfortable, excellent air quality, lots of warm, fresh air, natural materials, zero risk of condensation and mold, and quiet. And the flats will be monitored. So in a year's time, I can give you another talk telling you how, yet again, architects predicted something excellent and it didn't turn out. But I think we can be more confident than normal. There is a fact sheet, which if anybody is interested, we're working on a lot of other EnerPhits. All of these, I think, apart from the ones with all the thermal camera work, I think they will all go ahead. Not sure about the cross walls one. I don't think that will actually. But the others will. And so we should have quite a lot to be able to talk about soon. And that's it. Right, let me just.
Perfect. Well, thank you very much, Chris. I found that extremely interesting. I'm sure the others did as well. We have a shade over 10 minutes remaining, folks, if anybody has any questions. I've got a few written down myself, but I'm going to be polite and let the audience jump in first.
Please do.
Jose's asking in the chat, how were the works funded?
I'm not the best person for this because it got complicated, but it is a mixture of Scottish Government grant via the Housing Association, but there's quite a big chunk from Glasgow City Council as well. Glasgow City Council were drawn in because of the Scottish Funding Council money, which they were keen to support. So the Scottish Funding Council money went to two projects, a sort of new build modular thing in Edinburgh and a retrofit in Glasgow. And the retrofit in Glasgow was, I think they funded that with a view to COP being held in Glasgow. And so Glasgow City Council, I think, spotted the opportunity and thought they would support it as well. So it's a mix of Scottish Government, Glasgow City Council, Scottish Funding Council, and possibly other small bits, but that's the main bit. Cost per unit, I'm just reading from Jose's chat that I see. The original cost before, basically we did some initial checks on the building, but we weren't able to get into all of it initially. From the outset, what we did was we divided the costs into energy efficiency costs, sort of normal building related things like putting in new bathrooms and rewiring and things that housing associations would do anyway, regardless, not related to energy efficiency. And then there was a cost column for sort of big one-off things that were wrong, like the beams being rotten and the roof needing things like that. So when we started, it was about 85 a flat, 88 a flat. Well, the 88 a flat included the close, so I don't know what the calculation there is. But of that, about 32 was the EnerPhit. So about 32 grand of EnerPhit improvement. So all of the energy efficiency stuff was around about 32. That subsequently, that stayed the same, but the costs for the other things, the 80 grand went up because of just the extent of rot and decay, and all the ceilings fell down because they left it over winter when we said they needed to keep it dry, but the ceilings got damp and the plaster came off. So there was a huge amount of replastering that needed to be done, and that just put the prices up and up and up. So the eventual price was about, well, I think it's just over 100 grand a flat, which is daft. But a lot of that is wouldn't have been needed if the flats had been in good condition or had been kept in good condition, essentially. Echoing what I know Kenneth or Roger would say if he was in this meeting. But I mean, it's simply true to say that if you let the thing go out of hand, it becomes expensive to put it back again. But I think for the EnerPhit side of things, you can say it was about 32 grand, something like that. We've done a few now, and we're starting to see a pattern emerging of EnerPhit costs. So it's something between, it depends on the scale, but it's something between 25 and 50. The crosswalk ones were 50, but that was because they were individual properties dotted around a town. So you had to set up scaffolding and lift things into place, and there wasn't access because it was a modern estate and so on. So 50 grand a flat's quite a lot, a house quite a lot, but it was EnerPhit and it was individual semi-detached houses all around Paisley. Others have been about 25, 26. So it's that sort of thing. Is that about right, Jose? Sorry. I can't see or hear, so I'm assuming that was a perfectly answered. Oh yes, there we are.
Perfect. All right. Do we have any other questions from the audience before I jump in with mine? Oh, Kevin's got his hand up.
Hi there. I would be grateful if you would get back to the detail you showed us about avoiding putting the joist into the wall. My attention slipped when you were talking about it, and I didn't fully understand the detail you were presenting to us.
One moment. Right, Len, let me just share screen again. Just 1 second then. That was the rationale, and that is the detail there. Yeah. Is that what you were meaning, Kevin?
Yeah. That's exactly what I was wondering about. Yeah. So the logic was great from the graph, and this is a point where I lost attention.
So the way to introduce the subject was to say that if you look here, can you see my cursor?
I see it. Yeah.
Yeah, so one of the disadvantages of insulating on the inside is that you create an essentially permanently cold, wet stone wall. Yeah. And now the stone wall might itself not mind that much, but anything organic in there might well mind. So what we have to do is create a sort of nice dry situation like that. But what we did to check whether that would be true or not was this woofy calculation. And what that woofy calculation said was that on the north side, it didn't help as well that the Glasgow stone that is on the north side is much more permeable, much more friable, much more vapor burnable, absorbent of moisture. So we have this relatively high, well, they call it relative humidity. I think that should be moisture content, but anyway, this constantly high moisture content in that wall, because it is now it's separated from the warmth, and it's also separated from the ability to dry out on the inside. So on that basis, we were all trying to invent ways of sort of cheating by sort of reducing the insulation and sticking storm dry on all of these sort of things, which I think would have been a long-term disaster personally. But so in the end, we just said, look, we can't do it. I'm not prepared to take the risk. So we went to that. So the deal is that the joist used to go into there. You can just see the dashed line. So we cut the joist back. The contractor, interestingly, because I thought that we'd get howls of complaints from the contractors, but actually, I'd like to say they're not as dumb as they look. They knew that there were some advantages there, because what this allowed them to do was to run that air tightness layer straight down the wall without having to faff about around all the joists. So they didn't make any fuss about it, because I think once they realized they were going to be paid for it, and it was going to be a lot simpler to achieve the air tightness. So the air tightness line of plaster runs right down the wall. We then put that block of foam glass stuff in. We then bolt a sort of what I call a ledge beam. Everybody else called it something else. I call it a ledge beam. But and then you run the joists into that beam, and so there is no timber in the wall anymore. The only thing sort of touching that wall, which is cold and damp in theory, is a lime plaster. So I think that's pretty safe. And we've completely repointed the stonework on the outside in lime. So we're confident that as far as we can possibly achieve it, that any moisture in that wall will escape to the outside and can broadly escape slowly onto the inside. Does that make sense?
That's very clear. Thank you.
Okay, cool.
All right. I've got a kind of burning question, which I think I'd quite like to ask myself. There's a lot of kind of chat going around these days about taking a typology-based approach to retrofit, partly as a way to sort of reduce costs and increase standardization. So it's sort of kind of breaking the Scottish housing stock up into, well, let's say pre-1919 tenement, interwar bungalow, etc., and so forth. Yeah. And it's something that we're looking at internally. But it strikes me from listening to you, there's a lot of kind of interesting details, like the weird lead thing on the roof and the particular sort of thermal bridging that you get in that specific building, and the facing of the building, the lack of solar gain, the window sizes, all that sort of thing. Do you think a typology-based approach, do you think there's mileage in it, or do you think we're creating problems for ourselves?
No, there's definitely mileage in it. I mean, we do quite a lot of work. I would say half of my workload now is retrofit coordinator and retrofit designer through PAS 2035. And anybody who's in involved in that will know that they're all in, or they're into their names, that's for a start. But I mean, but yes, the typology approach, because in many cases you're dealing with, 300 houses that are exactly the same, so it's the typology approach is completely reasonable because so many buildings, not so much the older ones, but the newer ones of the 1930s, 40s, 50s, system built, somebody, all of these sort of interwar, post-war systems that everybody thought were brilliant, that they are identical in many cases, or at least they were. And insofar as they've been adjusted, they're still essentially identical in terms of what you need to do to them. So typologies make perfect sense. I mean, we did a project just recently down in County Durham in Bishop Auckland, and we provided the details for one house type, and I think they insulated 220 houses or something off that. Now, that's probably okay if they really are identical. We had to identify a few sort of nooks and crannies that might be different. It doesn't work when you're trying to do SAP or energy calculations, because if they're facing north or facing south or facing east, different sort of thing. But technically, I think it's a reasonable thing to do, as long as you've got your head about you. I mean, at the moment, we're in discussion, is the polite form of phrase, with contractors who want us to draw every house. So we're doing something in Argyll with Argyll Community Housing Association, which are all sort of houses on the islands, and they're wanting us to draw every single house individually, which is not what we were contracted to do. So we're just saying no. But their argument is that how can they possibly know what to do if they don't have individual drawings for every house? And my argument has been that they can't tell me that they're that incompetent, because if the house is fundamentally the same house design, it must be possible to know if this one's got extract ventilation in the bathroom and this one doesn't, and this one has a chimney for some reason and this one doesn't, and so on and so forth. I think a contractor is competent to make those decisions and say, look, this one doesn't seem to have a fan like it says on the drawing, so let's add a fan in, and then we just make that sort of allowance. I don't think that's that complicated. And I think if we're going to say the architect has to take liability and draw every single house in Britain, you take an expensive thing and make it an insane thing. Right, but I mean, that is my view. I mean, but I think what your point was to do with tenements and older tenements, and you could say, yes, a tenement is a typology, but actually, I mean, I've seen enough tenements to know that they're all made up as they go along. So who knows? Yeah, I think there's a risk there, but I think it makes more sense with the modern sort of system built things.
Okay, thank you very much. We're very nearly at 2 o'clock. If anybody has a quick final question, we could perhaps get it in. But not seeing any immediate hands, I think.
Yeah. Can I just raise
yep.
one slightly provocative question? Is there a cheaper way of doing this? I think the idea of actually spending 80,000 per unit per flat might be a bit daunting to some authorities. In Ireland, we have 700,000 properties that are in need of retrofitting. Is there some sort of a shortcut to near passive house that would actually achieve a lot of the results for a lot less money?
Yes. Well, yes. And that was why I was mentioning the ACB standard, because I think that is a sort of poor man's EnerPhit, really. In fact, I probably shouldn't say poor man, because I think it's quite a good idea. But yes, I think the answer is the ACB standard. That doesn't necessarily mean it will be cheaper, but certainly in the work that we've done, we can see that it doesn't push us as far down the sort of roads that when we're drawing it, we think, oh God, that's going to be so complicated, to do. When you're drawing things that you're making life difficult for people, or it's expensive. And there's been less of that with the ACB, because we can say, well, we'll just do such and such, because that will be fine, that will get us the numbers we need, and it won't be a problem, and they won't have to spend 6 hours hanging upside down to find something on the underside of the floor and so on. So yes, and then in terms of the cost, yes, but as I was careful to mention that the energy efficiency part of it was about 30. So I agree, £80,000 per flat's mental, and in fact it's more than that now. But of that, say 100 grand, about 70 of that is what I would call, well, it's not energy efficiency related, it's related to maintenance and, well, things like the beams being rotten and they wanted new bathrooms and so on and so forth. So I think if you're going to remember a number about EnerPhit, it's probably fairer to say 30, but you know, I know it goes up to more than that. And yes, I think the ACB is EnerPhit Lite for those who want an option.
Thank you.
Perfect. All right. Well, it's after 2 o'clock. I think we'll have to call it there. So many thanks again, Chris, for coming along and sharing your knowledge and expertise with us this afternoon. That's really interesting.
You're welcome. Yes, it does, is the answer to Karen Simpson.
Perfect.
Before I got cut off, I thought I'd better answer it.
Could I ask, is your book available, Chris? It looks very interesting.
Yes, it is. It's you can download it for nothing. It's free, or you can spend the princely sum of £10 and get it sent to you in hard copy. But you can download it from the CEDA website, so Scottish Ecological Design Association, or from the people who actually paid for it, who are the Pebble Trust up in the north of Scotland. But the CEDA guide, the CEDA website, you can get it from there, and you can download it for free as a PDF.
Right. Thank you.
So,
perfect. All right. Well, we're expecting to have another Energy Pathfinder webinar in a month or two. So keep your eyes peeled for an invite to that. But for this afternoon, once again, thanks to Chris, and I hope everyone has a very good day. Cheers all.
Thank you.